What do you think? I give you a hint. At this level, all I did was add a sphere to the space-time, which I've said here was of fixed size. So at this level, if I'm sticking with this equation up here, R is constant. Okay, so this is not the real black hole yet. This is a simplified toy model. Okay, but in this space-time that I've written down, this simplified toy model, there is only one size of sphere because I just stuck it in by hand. Right? This is not a physical space-time. It doesn't satisfy the vacuum Einstein equations, what have you, but just so we can learn how to read these things. There's only one size of sphere, so as the light rays propagate outward, as the sphere of light propagates outward, does it get bigger? No, it can't, because there's only one size of sphere. Okay, good. Great. And notice that that's true whether or not we consider the light rays that form the horizon or any other sphere of light rays, because there's only one size of sphere. Good. Now let's try this one. Okay? Let's ask the same question. What happens if I consider the sphere of light at xi equals 0? And an important thing here is to notice that if a light ray starts at xi equals 0, it will stay at xi equals 0, right? So then what happens to this sphere of light as it moves outward? Does it get bigger or smaller or stay the same size? Stays the same size. Because we've agreed that this controls the size of the sphere. And since this stays at xi equals 0, this doesn't change. So it stays the same size. So now we have, of course, the property that makes black holes interesting. So you might have said that you might have thought that the one thing I was holding back about was that surely this couldn't be a lot like a black hole because this light ray is clearly moving away, whereas perhaps you know in the back of your mind that light rays at a black hole horizon really don't get very far. Well, we see it's a consequence of this property we just mentioned. That what happens is that the space-time is such that even though those light rays are moving outward, just as this light ray is, it simply happens that due to the curvature of the space-time, the sphere of light does not get larger. Okay. On the other hand, of course, if I started outside the black hole, I'll try to use the same color scheme. If I started here, and if I looked at a light ray, which I can easily draw on my picture because I know how to draw light rays on this picture, we see that this light ray moves across various hyperbolae. It moves to larger and larger values of xi. So as long as this r is an increasing function of xi, all spheres of light that start outside the black hole, in fact, do get larger. And in that sense, become farther away from the black hole. Okay. Yes. We can also ask about spheres of light that start inside, but I'm going to save that for a bit later in the lecture. All right. If you don't like this, so geometrically what's happening again is the curvature prevents the sphere from getting larger. Or if you want to interpret this in more physical terms, what's going on is that although the light ray is trying its best to get away, the gravitational attraction of the black hole keeps the sphere from expanding. It's also useful to go through a similar story. Oh, any questions about that? Yeah? It's also useful to go through a similar story, not for light rays, but for these time-like observers that sit at other lines of constant xi. So let's imagine or consider the sphere at some other xi equals constant. Okay? So let's think about what these observers are doing. Again, if they sit at a constant value of xi, they're not getting any bigger. The sphere isn't getting any larger. So in some sense, they're not moving away from the black hole, right? On the other hand, we saw last time that, of course, an observer at constant xi is accelerating outward. Okay, so this is just the usual kind of way that gravity manifests itself in general relativity. Even though an object has a proper acceleration and is trying to, in some sense, move outward, it doesn't actually succeed in moving to a larger sphere. That's, again, just the, if you like, the gravitational attraction of the black hole, keeping these observers from flying away, even though they have a rocket turned on and are trying to escape. Okay? Oops. Same kind of story. All righty. Good. Great. Okay. Well, that was the physics. Now time for the math. So any questions about that before I move on? No? Okay. Well, now I'm going to follow the age-old tradition in mathematics everywhere of stopping what I'm doing, jumping to the final answer, and working backwards because it's easier. Okay. What I'm going to do for you is just to write down the usual solution for a black hole. So this is known as the Schwarzschild metric. With some work, one can show this satisfies the Einstein field equations, but I'm not going to do that here. But I'll start with this because many of you may have seen this equation even if you haven't worked through this material before. So it goes like this. The metric is minus 1 minus 2m over r times dt squared plus dr squared over 1 minus 2m over r plus r squared d omega 2. All right. And our goal is now to take this as given, and to show that, in some sense, near the horizon, this does, in fact, take the form that I've written over on the left-hand side. Okay? So it's useful first to inspect this and, as Tony said, not start our calculation until we more or less understand the answer. Okay? So if we look at this metric, it might first be useful to identify the horizon. Okay? Well, we decided before that the horizon is the place where the coefficient of the time-like term vanishes. So if we look over here at the time-like term, dt squared, there's a 1 minus 2m over r, which, as you can see, vanishes at r equals 2m. Oh, by the way, I should mention that here I have set Newton's gravitational constant equal to 1 to make my life simpler. Okay. So this should be the horizon of the black hole. If there's any hope to match this metric to the one on the right, then we'll presumably be matching r equals 2m with c equals 0. Yes. Good. All right. Next, what should we do next? Oops. Yes. So the next thing we should do is look at this and say, okay, over on that board, the distance away from the horizon is parameterized by this label xi, whereas over on this board, how far you are from the horizon appears to be given by this r. So presumably, what we want is r to be some function of xi. Now, which function is it? Well, let's find out by equating the appropriate terms in the metric. That is, if this is going to work out, this term here presumably should match with this term here. So let's hope that's true and work out the answer. We can then verify later that everything is going as planned. So let's write dr squared over 1 minus 2m over r is equal to dc squared. All right. Or in other words, dc is equal to the square root of r over r minus 2m times dr. I've merely swapped the two sides, taken a square root, and sort of cleaned this up by multiplying both top and bottom by r. Okay. Now, what we could do is be very clever students and work hard and do this integral exactly. but which can be done, turns out. But since we're only interested in my claim near the horizon of the black hole, let's do this problem in a more physicist-like manner, and again, expand in a Taylor series around r equals 2m. Okay. So let me introduce for you a new parameter delta, which is r minus 2m, in which case, taking a derivative, d delta is dr, since 2m is a constant. And I can now expand this in powers of delta. And I can write dc is equal to, on the top, well, r is 2m plus order of delta. On the bottom, we have r minus 2m, which is just delta. And then, of course, we have d delta. So the result is that I have the square root of 2m over delta, d delta, plus corrections of order delta. Okay? And now we have an integral that we can all do very easily. And we find that if I just integrate this, c is the integral of dc, say from 0 to c, which is going to be the integral from 0 to delta of the square root of 2m over delta d delta, which is therefore 2 times the square root of 2m delta. Okay. There we are. And what I want to do next, I think at this point, I really want to verify that this achieves my stated goal by going back. Well, let's write that one more time. Again, the black hole metric was minus 1 over 2m over r dt squared plus dr squared over 1 minus 2m over r plus r squared d omega squared. And if I now express this in terms of delta using my lovely formulae, what I find is that, let's see. Well, this is again, let's see. I guess I'll just clean this up first. This is r minus 2m over r dt squared plus dr squared over r minus 2m, and I'll put an r here, plus r squared d omega squared. Good. So now, oops, forgot the minus sign. What do we have here? R minus 2m is just delta. R is 2m plus some correction term, dt squared. This r is 2m plus order of r, or order of delta. Okay, that's that r. dr was d delta, so I have d delta squared. Oh no, sorry, dr was not d delta. Yes, it was.